Okay, so let's unpack this. We're seeing this incredible evolution with large language models, right? But really getting the most out of them, it goes way beyond just, typing in a good prompt. Today, we're doing a deep dive into something pretty groundbreaking, a concept that's really formalizing a whole new discipline for advanced AI. Context engineering for large language models. We're drawing on this really comprehensive news survey Lingre May and colleagues just published this July. It pulls together insights from, get this, over 1,400 research papers. So our mission here is to kind of pull out the critical nuggets from all that work, give you a shortcut to understanding how we can systematically optimize the information payloads these LLMs get, and well, what that actually means for where AI development is headed.
Yeah, and what's really fascinating, I think, is how this work moves way beyond just prompt engineering as we kind of know it. It defines a genuine scientific discipline. It's all about understanding and then optimizing the entire informational world an LLM operates in. That fundamentally dictates its performance. We're pushing past simple static inputs here.
That's a really key distinction. So maybe break it down for us. What exactly is context engineering? How is it fundamentally different from what most of us think of as prompt engineering?
Okay, so basically, instead of just throwing all the info into one big text string, context engineering sees the context, let's call it C, as this carefully constructed package of information. It's made up of different optimized parts, things like system instructions, external facts pulled in from databases, maybe definitions of tools it can use, even memory from past conversations, all assembled dynamically by a smarter system. The paper actually breaks down these components, gives them names like Sinsterts for those system rules, Sincere for external knowledge, think RG or knowledge graphs here. Then there's Keep tools defining APIs, Keep M for that persistent memory we mentioned, Sincere's capturing dynamic states like the user situation, finally Kakery, which is just the user's immediate question. So when you look at it like that, context engineering isn't just fiddling with the prompt. It becomes a proper optimization problem. We're trying to find the best set of functions that generate, retrieve, select, and assemble this context to get the highest quality output from the LLM, while still working within limits, like the context window size. This shift from traditional prompt engineering. It's huge. You go from context, it's just a static string, to this dynamic structured thing. You move from manually trying out different prompts to system-level optimization of these context-building functions. And crucially, it moves from mostly stateless interactions to systems that are inherently stateful, with specific parts for memory and current state.
Wow, okay, so it's like upgrading from just sending a text message to giving the LLM a whole meticulously organized briefing binder that updates itself constantly. That really is a different way of thinking about it. All right, let's dig into the building blocks then. The survey lays them out in three core areas, right? Context retrieval and generation, context processing, and context management. Can you give us the key takeaways for each?
Absolutely. So first up, context retrieval and generation. The basic problem here is simple. LLMs are trained on past data, but they need current relevant info to be really useful day to day. So beyond just crafting a prompt, this involves dynamically pulling together information, retrieving external knowledge. We see techniques like chain of thought, where the model reasons step by step, or even more complex ones like tree of thoughts or graph of thoughts, exploring different reasoning paths. But a massive leap, and something people hear a lot about, is external knowledge retrieval, especially retrieval-augmented generation.
Right, RE. That's where it goes out and fetches information.
Exactly. The LLM queries an external source, like a database or document store, finds relevant info, and weaves it into its answer. We're also seeing knowledge graph integration, like caping, letting LLMs pull structured facts based on meaning, not just keywords. Okay, second area, context processing. The big challenges here are dealing efficiently with really, really long sequences of text, refining the LLM's own outputs, and bringing in different types of data. You know how self-attention is core to transformers? Well, it gets computationally very expensive as the input grows. It scales quadratically, the ON2 problem. It needs tons of memory, tons of compute.
Yeah, that quadratic scaling is a killer for long contexts.
Right. So solutions are emerging from new architectures. State space models, like Mamba, are a big one. They process information more sequentially, much more efficiently for long inputs. We also see things like flash attention, which optimizes the attention mechanism itself, and techniques like yarn or long rope that help models handle context windows much longer than they were originally trained for. This area also covers things like contextual self-refinement. Frameworks like Self-Refine let the model basically critique and improve its own drafts. And importantly, integrating multimodal context vision, audio alongside structured data from things like knowledge graphs using techniques like graph formers or verbalization.
Okay, so processing is about efficiency, quality control, and handling diverse inputs. What about the third area, context management?
Right, context management. Here, the main issues are the limited size of the LLM's attention window. It can only focus on so much at once, and weird effects like lost in the middle, where information in the middle of a long input gets ignored. Solutions involve creating more sophisticated memory systems. MemGPT is a fantastic example. It acts kind of like a computer's operating system managing virtual memory.
Paging information in and out.
Exactly. It pages information between the LLM's limited active context window and external storage. This effectively gives the LLM a much larger working memory, almost like a long-term memory. We also see context compression. Techniques like an in-context autoencoder can compress the information going into the LLM significantly, maybe 4x or more. or streaming LLM, which allows models to handle theoretically infinitely long sequences by focusing on recent tokens. And even things like the heavy hitter oracle, which cleverly decides what information to keep or discard from the LLM's internal cache.
It really sounds like each of these areas tackles a fundamental bottleneck we've seen with LLMs. Retrieval gets the right info, processing handles it efficiently and refines it, management keeps it organized within limits. These pieces are impressive alone, but you mentioned they come together in system implementations. These aren't just lab experiments anymore, right? What are the main ways these components are being integrated in practice?
Indeed, they form the backbone of next-gen AI systems. We can group them into roughly 4 key categories. First, as we touched on, retrieval-augmented generation is probably the most widespread application right now. It bridges that gap between the model's internal, static knowledge and the dynamic external world. And it's evolving fast. We have modular RAG, like Flash RAG, which can flexibly combine different retrieval methods. There's agentic RAG, like Self RAG, where autonomous agents actually manage the retrieval process itself, deciding what to search for and when. And even graph-enhanced RAG, like HippoRAG, which uses knowledge graphs to perform more complex, multi-step reasoning across connected information.
Okay, so a RAG's getting much more sophisticated. What's next?
Second, memory systems. The whole point here is to let LLMs move beyond one-off stateless interactions, to give them persistence, something closer to human memory. We mentioned MemGPT with its OS-like paging. There's also Memory Bank, which actually draws on psychological theories, like the Ebbinghaus forgetting curve, to decide what information is important to keep versus what can fade. You can see how crucial this is for things like truly personalized chatbots or AI tutors that actually remember you and your progress over time.
Absolutely. That persistence is key. Third category.
Tool-integrated reasoning. This is about turning LLMs from passive text predictors into active agents that can interact with the world, basically giving them tools. This usually happens through function calling, allowing the LLM to access external APIs, run code, use calculators, search engines, databases, whatever is needed. We see systems like Toolformer, which learns how to use APIs through self-supervision, or frameworks like React, which stands for Reason plus Act. The LLM literally thinks through a step, decides on an action, like using a tool, takes the action, observes the result, and then reasons again. And specialized systems like Tora, which focuses on math problems by integrating with computational libraries.
So they become problem solvers that can actually do things. And the fourth category.
Multi-agent systems. This is where things get really complex and arguably very powerful. The idea is to have multiple specialized AI agents collaborating to solve problems too big for any single agent. This requires sophisticated ways for them to communicate protocols like MCP, which aims to be a standard interface, kind of like a USB-C for AI and A2A for direct agent-to-agent talk. And you need complex orchestration layers to manage which agents do what, how context is shared, and how they coordinate their actions. Frameworks like AutoGen and MetaGPT are leading examples here.
It really feels like we're architecting these intricate, almost living digital ecosystems for AI. It's fascinating stuff. But where does this leave us? What's the next big hurdle? The survey points to a really critical research gap, doesn't it?
It does. And it's a really important point. The survey highlights what it terms a fundamental asymmetry. Basically, even with all these sophisticated context engineering techniques, current models are becoming remarkably good at understanding very complex, rich context. But they still show significant limitations when it comes to generating equally complex, coherent, and factually grounded long-form output themselves.
So they can take it all in, but producing something equally sophisticated is still a struggle.
Exactly. We're getting great at feeding them this rich, dynamic context, letting them grasp intricate situations, but getting them to then say, write a detailed, accurate, multi-page report based on that understanding. That's still a major challenge.
Yeah.
This comprehension generation gap, you could call it, is really core focus for future work. It points towards needing next-generation architectures, much more advanced reasoning and planning abilities built in, and even more intelligent ways to automatically assemble and optimize the context itself.
So this whole deep dive into context engineering, it really shows that the path forward for AI isn't just about making models bigger and bigger. It's about getting much, much smarter about the information logistics. It's about building these really sophisticated context-aware systems that don't just process information, but truly understand, manage, and leverage it dynamically. That seems to be where the real leap in capability is coming from.
Absolutely. And thinking about that leads to a really interesting question, maybe something for you, our listeners, to ponder. As context engineering allows these LLMs to develop what look like increasingly sophisticated cognitive faculties, memory, tool use, reasoning over dynamic information, how do we actually design evaluation frameworks that can genuinely measure the emergent intelligence of these complex systems? Especially their ability to learn and reason effectively over the long term in messy, real-world environments. That's a whole challenge in itself.